Let's be real, the entire AI revolution runs on silicon. But not all silicon is created equal, not by a long shot. Today, we're diving deep into the two titans building the engines of AI, NVIDIA and Google. And this isn't just about who's got the better chip. They represent two totally different philosophies, and honestly, this competition is shaping the very future of what intelligence is going to look like. So this central question we're tackling here isn't just who is building these engines, it's how they're doing it. The choices these two companies are making right now are going to define the speed, the cost, and yeah, the very nature of AI for the next decade. The stakes are huge. And this slide, it just nails the core conflict. On one side, you've got NVIDIA, kind of like the arms dealer of the AI world. They're building the AI factory, these incredibly powerful do-anything GPUs that they'll sell to anyone. Then you have Google, the vertically integrated titan. They're building a custom AI hypercomputer, a bespoke, massive system designed first and foremost for their own empire and now for their cloud customers. We're talking two completely different playbooks. Okay, let's get into it. First up, AI's great compute divergence. And I want to be super clear here. This is not just a simple story of who has a faster chip. No. This is a profound, fundamental split in how you even think about designing a system that can create intelligence. And this is where things get really interesting. You can't just compare one NVIDIA chip to one Google chip. It doesn't work that way. The real difference is the fundamental unit of compute. For NVIDIA, that unit is the single, beastly, powerful GPU. But for Google, the unit is the entire pod, a whole supercomputer where thousands of their chips act like one single cohesive organism. And trust me, that changes everything. So that idea, that difference in the unit of compute, it leads us right down to the philosophy of the silicon itself. I mean, these chips were born from completely different histories, and they are absolutely optimized for very, very different goals. Okay, so here is the best analogy to keep in your head through all of this. NVIDIA's GPU, it's the Swiss Army knife. Seriously, it evolved from making video games look awesome, so it's incredibly versatile. You can program it to do almost anything. Google's TPU, on the other hand, is the scalpel. They started with a blank sheet of paper and designed a chip for one thing and one thing only, the crazy matrix math that is the beating heart of all modern AI. So what exactly makes the TPU a scalpel? Well, it comes down to this core piece of tech called a systolic array. See, a traditional GPU has to constantly run back and forth to its memory to grab data for every single calculation. A systolic array is different. It's a grid of processors that just passes the data directly to its neighbor. That heartbeat analogy is perfect. It just rhythmically pumps data through the whole system. And this simple-sounding idea, it radically cuts down on data movement, which saves a massive amount of energy. So how does that heartbeat actually work? Okay, imagine this. First, the model's brain, all its weights and knowledge, gets loaded into this grid of processors and just stays put. Then your data, say your question for a chatbot, flows in from one side like a wave. It ripples across the grid, interacting with those stationary weights. As it moves, the results build up and the final answer just flows out the other side. The absolute key here is that the data gets reused over and over without that costly trip back to memory. That's the secret sauce to its efficiency. So you're probably asking, how in the world does the Swiss Army knife compete with that level of specialization? Well, NVIDIA's answer is what I'd call elegant brute force. They built specialized little units inside their general-purpose GPUs called tensor cores, which are just for that matrix math. And then they added this brilliant feature called the transformer engine. Get this. It automatically figures out when it can use less precise numbers to do the math, which can literally double the performance. And the developer doesn't have to do a single thing. It's genius. And that brute force approach? It gives NVIDIA one massive, undeniable advantage: memory bandwidth. I mean, just look at these numbers. They are staggering. The new Blackwell B200 has 8 terabytes per second of bandwidth. For something like a chatbot, where you feel every millisecond you have to wait for a reply, this is everything. More bandwidth means a faster time to first token. It's that feeling of an instant, snappy response. But there's always a but, right? All that power, it's hungry, really hungry. A single B200 chip can pull over 1,000 watts. And this is where Google's specialized scalpel design just shines. The new Trillium TPU boasts a 67% improvement in performance per watt. Now, when you're running a data center with tens of thousands of these chips, that's not just about being green. That translates into millions and millions of dollars saved on your electric bill. And just to really hammer home what we mean by NVIDIA's brute force engineering, get a load of this number, 208 billion. That's how many transistors are in a single B200 GPU. They actually hit the physical limit of how big you can make a single piece of silicon. So what did they do? They just engineered this insane way to fuse two of these massive chips together so tightly that to the software, it looks like one single monstrous GPU. It is an absolutely incredible feat of engineering. And that idea of a single monstrous GPU, well, it brings us perfectly to our next section, building the AI supercomputer. Because let's face it, in the era of models with trillions of parameters, one chip isn't enough, no matter how big it is. The network that connects all these silicon brains into a single cohesive mind is just as important as the chips themselves, maybe even more so. And guess what? The philosophies here are once again polar opposites. NVIDIA's approach is the scale-up monster. Their NVL72 rack is designed to take 72 separate GPUs and trick them into acting like one single gigantic GPU. It's all about maximizing performance for one enormous job. Google's approach is what we're calling the hyperscale organism. Their TPU pod is designed to make the entire data center the computer, prioritizing things like resilience and being able to efficiently scale for thousands of different jobs all running at once. Now, Google has a secret weapon here, and it's all about the network. First, their chips connect directly to each other in this cool 3D mesh, which means they don't need a bunch of expensive external switches. But the real game changer, the thing that is just wild, is called optical circuit switching. It literally uses tiny mirrors to physically redirect beams of light carrying data. Why is that cool? It means if a chip fails in the middle of a month-long training run, they can instantly reroute the network around the dead chip and reconfigure the entire cluster on the fly. That is a massive, massive advantage for reliability. All right, we've talked silicon, we've talked systems, but now we have to talk about the battlefield that might matter more than all of it combined. Section 4, the software war. Because here's the truth. Your brilliant hardware is just a really expensive piece of sand if the software can't use it. And for years, this has been NVIDIA's unassailable fortress. And this quote right here, it gets to the very heart of NVIDIA's dominance. It's something people call the CUDA moat. See, CUDA is NVIDIA's software platform. And for nearly 2 decades, basically every important, cool, custom piece of code for AI and scientific computing has been written in it. If you're a researcher with a new model architecture, you write it in CUDA and it just works, period. Trying to port that over to a TPU has historically meant a complete, painful rewrite. And that friction, that barrier, has been NVIDIA's greatest defense. But you don't take on a giant like NVIDIA without a plan. And Google has been playing the long game, patiently, methodically, building a bridge across that CUDA moat. It started with their own framework, JAX, which talks perfectly to their hardware. Then they poured resources into making PyTorch, the world's most popular AI framework, run great on TPUs. But the real breakthrough, the thing that made everyone sit up and take notice, was getting VLLM ported over. That's the industry standard tool for running models efficiently. This was an absolute game changer. Suddenly, deploying your models on TPUs got a whole lot easier. Okay, so we've laid out the battle lines on hardware and software, the whole shebang. So what does this actually mean for you, for someone who's building AI stuff? Let's distill all of this down into a practical guide. When do you pick one ecosystem over the other? All right, so you're going to go with Team NVIDIA if speed and flexibility are what you care about most. We're talking about those super responsive chatbots where every millisecond counts. You'll pick it for cutting-edge research, where you need the absolute freedom of CUDA to write custom code. It's also the choice for workloads that need to run anywhere, on any cloud. And of course, it's for training those massive frontier models where you're in an all-out race to get the answer and cost is no object. So when do you pick Team Google? Well, you're going to lean into the TPU ecosystem when your main drivers are scale and efficiency. This is for training those huge models where the total cost of ownership and the power bill are critical factors. It's for high-throughput jobs, like, say, analyzing millions of images, where the total number you get done per day matters more than the speed of any single one. And of course, it's a no-brainer for teams who are already deep in the Google Cloud world and can really optimize for that native architecture to get some incredible long-term gains. You know, in the end, this whole battle, this great compute divergence, is actually fantastic news for all of us. It's what you want to see. Google's focus on efficiency and scale forces NVIDIA to keep pushing the performance envelope, and just as importantly, to be more competitive on price. And NVIDIA's raw power and huge software lead forces Google to make its own ecosystem easier to use and more accessible to everyone. Competition is a good thing. And that leaves us with one final massive question to chew on. As AI continues this absolutely explosive growth, what is its future actually going to be built on? Will one philosophy win out? Will it be a single universal engine like NVIDIA's Swiss Army knife GPU that can just do everything pretty well? Or are we moving towards a future that's powered by a highly specialized, massively interconnected global brain, like the one Google is trying to build? The answer is still being written, and it's going to be fascinating to watch. Thanks for tuning in.